welcome to lecture 26 of Fox, and we're going to be talking about Turing Machines, which is our final model of computing. Okay, and in fact, it is a model of the digital computer. Now, this lecture is so important, it almost warranted the arrival of Orange Malik, but we're saving up Orange Malik for one more lecture, so he didn't quite make it to today's lecture. But okay, let's have a quick recap of what we did last time. So last time we talked about context-free grammars and the relationship to, DFAs with stack memory or push-down automata. Okay. And the basic idea is that context-free grammars generate languages, and those languages can more or less be solved by digital finite automata, DFAs, with stacks. Okay. But then, there were several problems that we mentioned that cannot be solved by context-free grammars, cannot be solved by digital finite automata with stack memory. And the fundamental reason why they couldn't solve those problems was because they didn't have access to every memory location. They only had top access to the stack. Okay. And so that's going to be our cue to how we enhance the model and end up with the Turing machine. We want a new model which is basically a DFA, but the memory is not stack memory, but random access memory, or what we like to call RAM. Okay. Now, so these are the machines that, basically Turing invented, and nothing has really changed in any significant way since he invented them. So, we're going to more or less be following in the footsteps of the great Turing. In 1936, here's what he did. Okay, and this is, an example of just the beauty of pure thought. Okay, so what did Turing do in 1936? He sort of invented a notion of what it means for a number to be computable. So there are computable numbers and non-computable numbers. Well, a number is basically, computing a number is just a computing problem. So there are problems that can be, solved, and problems that are not computable, that cannot be solved by a computer. So in this process, he invented the computer. He invented and used subroutines. He invented the programmable computer. And then he answered some hard problems that nobody else was able to answer. Okay. And he did all of this. Invented the computer, subroutines, programmable computer, all of this purely in his mind. He did all of this before the world even saw its first computer. And this is the model of the digital computer that we have now. So what's all this fuss about the Turing machine? Okay, and that's what we're going to discuss today. We're going to discuss Turing's machines. And basically, they're DFAs with random access memory. Let's go to the board. Let me tell you about Turing's machines. Okay? And I have a picture of what a Turing machine might look like, and this is one version of a Turing machine. And essentially, it's a DFA with random access memory. Okay? So let me tell you about what's going on in this picture. So we have our DFA, our CPU. Think of it as the CPU. It's got states, and it can transition among states. Okay? And then remember, we've endowed now the DFA with not stack memory, but random access memory, which we represent as a tape. Okay? And this tape is, as long as you want to make it. So it's unbounded. So in some sense, the DFA has access to as much memory as it wants. Okay? So it's a little more powerful than the computer that's sitting on our desks, but that's okay. Okay? Now, as usual, in order to sort of read and write to this tape, okay, there's a read-write head, and this tape has memory locations which are indicated by these rectangular slots, and in each memory location we can write various symbols. Okay, now the default symbol is the blank symbol, which is this little caret. Okay, but there are all kinds of other symbols that we could write. So there's a red star. Okay, with this we're going to think of this guy as a beacon symbol, a landmark. So this is always there. And then there are bits, zeros and ones. There's a punctuation character. So there's a bunch of symbols written on the tape slots. Okay. Now, by default, we will assume that the symbols are the blank, zeros and ones, because we're in binary, maybe a punctuation symbol or two, and the beacon symbol star. Okay. Now, how does the DFA access these various memory locations? It's got a read-write head. It can move left or right. Okay, and that's the main capability that the DFA has now acquired. It has acquired the ability to move left or right to access various locations on the tape. Okay. Think of the CPU as sitting on some kind of a rail, and it can move left or right. Okay, and now, if you remember back to our old friend, the DFA had a read head, and it started at the input's first bit and read the input one bit at a time until it came to the end. So where's the input here? There's no read head again for the input, although you could have one. Because we have an unlimited tape, we might as well put the input on the tape. So think of, the tape as starting off with the beacon symbol, and on the right of the beacon symbol is the input. Okay. And, to illustrate, I put the input 001, pound 001. So this is in the language, W, pound, W, so repetition. And I picked this language to start off with. We're going a bit ambitious because, remember, there was no DFA with stack memory that could solve this problem because you need access to the bottom of the stack. Okay? And because context-free grammars and DFAs with stack are basically the same, there's no context-free grammar that can generate this language. Okay? And we're going to straight away show that effortlessly, this DFA, which is endowed with the ability to move, and a tape memory, which is random access, can easily solve this problem. Okay, so let's develop the high-level algorithm that solves this problem using this new capability that we have. So there's nothing unexpected here. You've got a random access memory, which means you must be able to move around to access it. Okay? And other than that, you basically have a DFA. Okay? That can read from your memory. It can write symbols to the memory. And it can do some, slightly fancier things, like it can mark various locations, okay? And we'll see how marking helps, okay? So all of these, capabilities, you can think of them as enhancements that are convenient. So we're describing a specific version of the Turing machine. The absolute most basic Turing machine just has, a beacon symbol that can be represented in some way, and only zeros and ones and the blank. But all of these versions of the Turing machine are equivalent, so we might as well choose one that's convenient for us, that makes it easy for us to describe the workings of the machine, okay? So that you can just get the high-level idea of what's going on.